Okay, so we are talking about characteristics of four-bar mechanisms, and four-bar mechanisms can be classified according to their motion. Probably the most common is the crank rocker, in which you have the link 2 makes a full rotation, okay? And the rocker makes a rocking motion, like a swinging motion like this, which you can see, for example, in cars, windshield wipers. Okay, it goes back and forth like this. But that's not the only possible four-bar mechanisms. There are other possibilities. For example, besides crank rocker, you might have a double crank in which both links rotate, or you might have a double rocker in which both 2 and 4 links swing and oscillate. So they both do this kind of motion, and you cannot have a full rotation. So if you connect a motor to a double rocker mechanism, you will break the mechanism, okay? It cannot really turn, it's impossible. So S is the length of the smallest link, let's say, whatever that link is. And let's say that the L is the length of the largest link, and P and Q length of other 2 links, let's say. Now, we have the Grashof, the famous Grashof condition, which states that if this is true, if S plus L is less or equal to P plus Q, the smallest plus the largest is, let's say, less than length of smallest plus largest is less than the length of the middle links, then if this condition is satisfied, okay, then we can say the following. I will illustrate this with a video, but at least, if this is satisfied, at least one link makes a full rotation, if the Grashof condition is satisfied. Let's try to see this through a, let's say, video, so that I will search something over the internet. Okay. Okay, let me share this video with you. Let's watch it together. It's kind of longish, but I think it's quite informative. So let's try to understand. I will try to talk behind the picture, actually. What is this?
Hello there, guys. In it,
And, okay. So let's stop this recording. Sorry, this stop sharing. Let's share the YouTube. So you can see it, I suppose. Grashof's law video. I will just let you watch it, and in the meantime, if necessary, I will talk in the background.
video, we will discuss about Grashof law. Do you know that four-bar linkages behave in different manners? And no, look at these four-bar linkages. What information can you infer from these linkages? These all are very similar. Exactly, but they behave differently. How? And next, I can swing my both arms. I can rotate my one arm.
You see, this is a crank rocker, for example. The other one was a double rocker.
I can rotate my both arms.
This is a double crank.
That's amazing. Can you guess the reason behind their different behaviors? Yes, it must be due to different lengths of the links and depending upon which link is fixed. Correct. Is there any relation for this? Yes, it is known as Grashof law. Grashof law. What's that? Let's discuss it. Grashof law. Consider the four-bar mechanism. S be the length of shortest link. L be the length of longest link. P be the length of remaining one link. Q be the length of the remaining other link. By Grashof law, for at least one link to be capable of making a full revolution, the sum of the lengths of the smallest link S and the largest link L is less than or equal to the sum of the lengths of other two links, that is P and Q. Got it. The condition can be broken in two parts. First, S plus L is less than P plus Q. Second, S plus L equals P plus Q. Exactly. What if sum of shortest and longest link is greater than the sum of other two links? For S plus L greater than P plus Q, no link will be able to make a complete revolution. The mechanism so obtained is known as triple rocker mechanism. Yeah, all the three links other than fixed link are actually. Exactly. Now, we will discuss the Grashof condition. We wrote the condition in two parts. First is S plus L less than P plus Q. And so, shortest link is adjacent to fixed link. The mechanism so obtained is known as crank rocker mechanism.
Okay. Now, if
Doesn't
the
matter which link is fixed. Fixed link can be any of the other three remaining links.
if the shortest link is next to the fixed link,
Fixed link
then you have a crank rocker.
obtained is known as double crank mechanism.
If you fix the shortest link, you have a double crank.
Matter? No, the position of other three links won't affect the nature of the mechanism. This three, shortest link is opposite to the fixed link.
In this case,
Mechanism so obtained is known as double rocker mechanism. Can you tell which link is rotating in this mechanism?
you see, still there is a rotating link.
Which is also the shortest link. Correct.
The green link is rotating, as you see.
The condition S plus L less than P plus Q. Can you summarize the three cases? Yes. Case one. Link adjacent to shortest link is fixed. This configuration is crank rocker mechanism. Case two. Shortest link is fixed. This configuration is double crank mechanism. Case three. Link opposite to shortest link is fixed. This configuration is double rocker mechanism. Before discussing the second part of Grashof condition, we will discuss about inversion. Inversion is created by grounding a different link in a chain of a chain. There are as many versions of a given linkage as it has links. So, for S plus L less than P plus Q, we have four inversions of which three are distinct inversions. First, crank rocker, which is obtained by grounding either of the links adjacent to the shortest link, so they are two in number. Second, double crank, which is obtained by grounding the shortest link. And third, double rocker, which is obtained by grounding the link opposite to the shortest link. Now we proceed to discuss the second part of the Grashof condition. Can we tell what it is? Yes, it is. S plus L equals P plus Q. Correct. In such type of kinematic change, the links become collinear at least once per revolution of input crank. All linear? What does that mean? Like this, all the links are along a straight line. Got it. Linkage. The lengths of the links are distinct. For example, F 1 unit, L 4 units, 2 units, Q 3 units. All the inversions obtained are same, and in the case S plus L less than P plus Q, which are crank rocker, for which link adjacent to shortest link is fixed. Double crank, for which shortest link is fixed. Double rocker, for which link opposite to shortest link is fixed. Linkage. Length of two links is same. For example, P equals S equals 1 unit. Let L be 4 units. Now to balance the equation, Q has to be equal to L, that is 4 units. So we have two pairs of equal lengths. In this case, links can be joined in two ways, equal links opposite to each other. The linkage so obtained is parallelogram linkage. Another way is equal links adjacent to each other. The linkage so obtained is deltoid linkage. All the inversions are either crank rocker or double cranks for this case. When the links become collinear, both the linkages suffer from change point condition, that is, the output behavior becomes indeterminate. This is because the linkage may assume either double crank configuration or crank rocker configuration at each position, which is unpredictable.
Okay, these parts are not
With the help of an example,
too easy to understand, but I will try to explain it.
note that link A is the input crank. Like simulated, as the crank rotates, the links become collinear. This is first change point condition. Now, at this position, motion of link B becomes unpredictable. It can go either of the two ways. Now as the input crank, that is, link A, rotates further, links become collinear again. This is second change point condition. Motion of link B is again unpredictable at this position. It can go either of the two ways as shown. So, this was all about Grashof law. Hope you enjoyed this tutorial and understand the behavior of four-bond linkages. Yes, now I do understand about it. But wait, I haven't seen that. Can you elaborate a triple rocker mechanism and how is triple rocker mechanism different from double rocker mechanism? For that, you should go through these videos.
Okay, there are other videos, it seems. Let me just show you another simple video like this. This is a, you see, crank rocker mechanism. This is the most common mechanism actually we see. Okay, then let's stop this and share our screen. So, crank rocker is happens as we see just here. S is next to the fixed link. Double crank happens S is the fixed link. And double rocker happens when S is opposite to the fixed link. Okay. So this is the Grashof condition. If the Grashof condition is not satisfied, you cannot claim that there is a full link that makes a full rotation. In the double crank mechanism, for example, S makes a full rotation. Sorry. In the double crank mechanism, which is something like this, for example, this is the S link. Well, let's say this is the longest. This is the Q. This is Q. L and P make full rotations here. Well, no. I'm sorry. This is double rocker. Well, L and P make rocking motions. S makes a full rotation motion. Okay. And another possibility is, as I have said, the opposite of this, which is this one. Let's say. So S is the fixed link. S. Let's say L, P, Q. And this is, excuse me? This is double crank, yes. In that case, P and L make full rotations, okay? This is a fixed link. So these are the mechanisms that satisfy the Grashof condition. If you don't satisfy the Grashof condition, none of the links make a full rotation, but that's another thing. Also, in the case of equality, you have linkages behave a bit like, just like here, if they are not forming a parallelogram. If they form a parallelogram, that's a different matter. Okay. But we don't encounter these things too much in the practice anyway. Okay. But usually the four-bar mechanisms are designed so that they obey the Grashof condition. I'm not going to talk too much about this. Just remember the Grashof conditions and in which cases of the Grashof condition you have crank rocker, double crank, or double rocker mechanisms. Okay, you have to know this much. And I try to illustrate it with a video over that. Actually, there are quite nice websites which show, illustrate four-bar mechanisms. Let me try to find. Anyway. This is the rest we just, you don't, the ones in the There is so so much for the Grashof condition. Let me continue now. Again, let's try to look at the position analysis of a four-bar mechanism again. Let me try to draw it again for you. Well, this angle is called the mu. Mu is called the transmission angle, as we know. Now, in order to solve for the four-bar mechanism, as you might remember, we did something like this. We connected it with a fictitious line that has a length of S. Okay. Now we divided, as you see, the four-bar mechanisms into two triangles here, from which we can solve for the unknowns. We give certain names to these angles actually. This one we call, if you remember, was psi, and this whole this whole angle we call it phi, and this one was called phi prime. So we have two triangles, the triangle of A0, A, B0, and the triangle of A, B0, B. So using these triangles, actually we can use, and using sine and cosine theorems, we can find the following. For example, for triangle A0, A, B0, you have A1, A2, theta 1, 2 is known. Okay. That is A2, A1, and theta 1, 2. So in a triangle, what do you need to know? Well, two sides and an angle is enough to, determine a triangle. So you can immediately from here find, for example, S is equal to, from the cosine theorem, very simple, a1 squared plus a2 squared minus 2a1 a2 cosine theta 1 2 to the power 1 over 2, for example, gives you this distance S. And phi prime, for example, can be obtained either from sine theorem or from cosine theorem. Let's say we use cosine theorem, cosine inverse of a1 squared plus s squared minus a2 squared over 2a1s, if you remember. So this thing is solved, this triangle is solved. Maybe you can find this angle, but it's not necessary. For the triangle A, B0B, A, AB, B0, AB, B0, AB, B0. Well, it's the same thing anyway. Now, S is now known. A3, A4 is known. What is unknown here? Well, you know all the three sides actually here, right? So A3, A4, S is known. So the new angle can be determined from this plus minus. We talked about this plus minus before. A3 squared plus A4 squared minus S squared divided by 2A3, A4. And this mu is called the transmission angle. Okay. And there are two possible values. One is for the normal configuration. The other is for the, cross configuration of the mechanism. I had shown this. And then phi is equal to cosine inverse of, again, A4 squared plus S squared minus squared over 2A4S. Okay, now what we want to do in this mechanism, as you know, is to find there's one more thing here I didn't write here. Phi is equal to pi minus phi prime. I will skip this. And then we want to, if you want to find theta 1, 3 and theta 1, 4, theta 1, 4 is pi minus psi, and theta 1, 3 is 4 minus mu. So if you want to solve for these, you can find them out from as you see, for the 4-bar mechanism. This is the so-called stepwise solution, let's say, for the 4-bar mechanism. Stepwise solution. As you see, I didn't use the loop equations or anything for the 4-bar mechanism position analysis here. We just use the solution in steps. We first solve for S, then phi prime, then phi, then mu, then psi, and then theta 1, 4 and theta 1, 3. This is how you can, well, it's quite easy to, for example, computerize the possible position analysis technique to for the four-bar mechanism. Okay. Yes.
So is this the stepwise solution just for four or?
No, actually, previously I had shown you other examples. For example, for the slider crank, it's possible. Well, a slider crank is even easier than this. Actually, I can do that. But then the other solution we tried to do was the analytical kind of solution for the position, which was a little bit harder. If you remember, we wrote that Freud-Einstein equation and so on, and you get the solution in one step. But this kind of stepwise solution techniques are possible, but they require some intuition. You cannot really do this. Well, there is no general method for this, okay? You have to use, as I said, lots of trigonometry and properties of triangles in order to get the solution. What can I say? As I have said, sorry, not this one. Let me carry this here. On this part, let me draw the cross position of this mechanism as well. For example, the cross position is something like this. Let's say so in this case, we have kind of the similar mu here. This is that would be the mu. Okay. So that's why we have the plus minus terms here. Okay. Okay. Well, I am going to solve a problem. What happens? But we don't have time for that. So let's take a break here and let's come back and let's do that the next time. Okay, so let's take a break here. Check this. This website has a simple four-bar linkage simulation. For example, here in this case, we have a crank. The blue one is the crank and the red one is the rocker. And the connecting rod, the green one, makes a rotary motion, and some point on it makes this strange, interesting motion. I don't know what this configuration space is, but you can play with the link lengths, for example, and change the possible motions. For example, now it has become a double crank mechanism, as you see. I can even make it smaller. I have grounded the shortest link, as you see. This is a double crank. If I make this shorter, for example, it will be a double rocker mechanism, as you see. And some mechanisms are impossible. They don't. This is a crank rocker again. And so on. There are possible configurations. There are certain mechanisms that obey the Grashof condition, and some of them don't obey the Grashof condition. For example, this is a non-Grashof mechanism, which is a double rocker. You see, you don't want double rocker mechanisms because you cannot really power them with an electric motor or any kind of motor, because they have to make, both of them have to make rocking motions, but they might be useful for other purposes. I don't know what, but all sorts of strange motions, as you see, are possible as with these 4-bar mechanisms, as you see. All these have been, well, analyzed. But if you want, the website is here. You can try to check it yourself. Okay, that's all I'm going to say about this. Now let's continue with our thing. Okay. Now I wanted to solve you one more problem, and that has to do with, again, that is from actually Eres Söylemez slides. I would like to copy it to you from here to here, but unfortunately I cannot. This whiteboard doesn't accept copy and paste. I couldn't find a way to do it. So I will have to draw it, which is not very easy. I think this is a mechanism used in some kind of textile machinery. So let me draw it as much as I can. As well as I can. And then there is This is actually from Eres Hoca's slides. You can see it from velocity acceleration analysis slides. I have put that in Hot to Class so you can find out the original one. So this is a this is it's rotates. Why am I not using this again? This is S12. So the links are, the ground is 1, this is 2, this is the 3rd link, and this is the 4th link. The 4th link is just makes a rotation, as you see over here. It's not. So you have S12 distance. S12 is the given quantity. Okay. And S43 and S, not S, but theta 14 are the variables to be found. We don't know them. It depends on the position of S12. Now, we want to just a second.
What's the S12?
Huh?
What's the S12 then? What's the baseline?
Baseline is the bottom point of this link too. Okay.
So there's an extended mechanism as well.
What do you mean extended?
Well, because you're taking S12 from the baseline.
No. This is just ground. It's a reference point. From the reference point, you take a distance, whatever that reference point is. Okay. Now, let me draw it in some other color, which will not be too difficult to see. Let's say let's call this point A. Let's call this fixed point B0. The intersection of horizontal and the vertical from B0. Let's say they intersect at A. Okay. Excuse me? A0? A0, this is A0, sorry. A0. Now, this distance between AB0, I will call it S. Okay. And this angle between here to here, I will call it phi. Okay, now once we do this, we will try to analyze this mechanism. So, first of all, this S distance is important, kind of. So this B0A, sorry, which I will call S, is, we have to give certain names to certain variables. By the way, let's do that also. Okay, the whole thing. This is all done in the picture, but I have to do it again. This whole distance is A3. Then let's say this distance between here and here is called A1. This distance is called too much time actually. This is A2. I wish I could have done it. There is one last thing. This distance, which I have here. Okay. Is called B1. Okay, it's complicated enough. So Now look at this S. S is equal to, well, look at this triangle. If you want to find this S is equal to square root of b1 squared plus, now, what is that? This a0, b0. What is a0, b0? A0, b0 is, where is a2, a1, and s1, 2. If you, okay, you have s1, 2 plus a2 gives you this whole distance. If you subtract a1 from it, you will get the a0, b0 distance. So it will be s1, 2 plus a2 minus a1 squared. Okay. And the phi angle, this angle, it's an external angle, but you know, it is, it can be found from tangent inverse of minus b1 over b1 is b1, b1 is distance, a0a. Again, s1, 2 plus a2 minus a. Okay. Okay. Now, why do we need S here? Because we have another triangle here, which is this one. It's not a good color. This one. So this is S4 S43 here. This is A4 here, and this is S, as you see. That's a right angle triangle. So you can write, for example, S43 is equal to square root of S squared minus A4 squared. Okay. And this angle is the angle I will call psi. Psi angle is and if you look at it, theta 1,4 is phi minus psi. Okay, theta 1,4 therefore can be determined. So what were we looking for? We were looking for S43 and theta 1,4. So these are the unknowns we needed to find. Okay, and they can be found from the geometry rather in a straightforward manner. It's not too difficult. You just use some triangle relationships as you see. But if you want to somehow, since this is a mechanism with a, let's say, point, you would like to find the position of this point, position of C. You can write that to be position of RC, for example, as S12 plus A2 is here, this vector, plus this vector, AC vector, which I can write as A3 times e to the I, theta 1, 4 minus pi over 2. Okay. Is this understood? This is a little bit difficult maybe. Let me try to draw it here. So you write this vector upwards and then this vector. This is point C. Okay. Since theta 1, 4 is this angle, theta 1, 4, okay. If you subtract pi over 2 from here, you will get the angle of this thing. This thing is theta 1, 4 minus pi over 2. Because it's in the, it's a negative angle, therefore it's in the counterclockwise direction. I is the I is the imaginary number, so you can write RC to be, let me write it again, I S12 plus A2. Now this is e to the minus I pi over 2 means multiplying it with minus I A3 e to the I theta 1, 4. Okay. Are there any questions about this? This is how I use it, e to the I theta 1, 4 minus pi over 2, I'm sorry, is equal to e to the I theta 1, 4, e to the minus I pi over 2. And this is minus I. This is minus I. That's how I obtain this point. Okay. Okay. After this, maybe you would like to see this a little bit more. We want to find the x and y coordinates of we want to find the x and y coordinates, let's say x and y coordinates of C. So XC is equal to the real part, real of RC, which is A3 sine theta 1, 4, and YC is the imaginary part of C, which is S12 minus A2 minus A2 cosine theta 1. So this is RC can be written as XC I, let's say, as a vector plus RC. So this is the position. Okay, to find the velocities and accelerations, we have to write a loop equation. And to write the loop equation, let me go back as if it's not too complicated. I have to write a loop here. Let's call this point O. Okay. We have to give names. Let's call this O prime at this point. So OA is equal to OO prime plus O prime B0 plus there is a, if I give a name to this thing, so let me write it here so that you can see it as well. OA vector is equal to this vector is equal to OO prime vector plus O prime B0 plus B0C plus CA. Okay. So this is equal to this plus this plus this plus that. Okay. That's a long expression. Let me erase this part and write it here so that S43, this one, S43, in the negative direction. E to the I, theta 1/4 plus pi over 2. Okay. Theta 1/4 plus pi over 2 is the angle of CA, as you see. But we can write this as I S43 e to the I theta 1/4. So this is our loop equation. Okay. Now let me go to here.
Shouldn't there be a plus 80?
Let me see.
No, not the next.
Here you mean?
No, the next slide. Next slide.
Next slide.
Next slide.
Here.
The imaginary device, shouldn't it be plus 80?
That should be a plus 80. That's right. Okay. So the loop equation, I will write this again, collecting the I terms. I S12 plus A2 minus A1 is equal to E1 plus A4 plus IS4 3 e to the I theta 1. Actually, it comes out to be not too difficult, okay? The loop equation is this one. And there are many constants here. So when we take the velocity equation, or if you want to find the velocity, you just take the d by dt of the loop equation. And what you get is the following: IS12 dot is equal to, well, A2, A1, B1 just cancel. I A4 omega 1 4 e to the I theta 1 4 plus IS4 3 dot e to the I theta 1 4 minus omega 1 4 which we can write as follows. I omega 1 4 parentheses. But there is an I here, right? If I didn't make a mistake. Yeah. Just a second, what happens? I'm taking the derivative of this. A4 e to the, okay, this is okay. This is okay. I comes here. Yeah, that's all right. Okay, now this is a bit confusing. I times I gives you a minus one. That's how we put it here. Plus I times 4 that's e to the So what does this mean? S12 dot is, let me go back here. Velocity of S12 dot is the velocity of link 2 going upward or link 3 going upward at point A. So this is, I can say that this is VA2, but this is equal to VA3. Okay. Now, what is this? This is, if you want to understand, this is the velocity of A on link 4. If link 4 were to be extended, okay, which is link 4, as you might remember, is this link that rotates like this. That would be the velocity of that link, and this would be velocity of A3 relative to A4. Here, with this equation, we would like to solve for S12 dot. You would like to solve for omega 1,4 and S43 dot, okay? Which is not too hard, by the way, because these equations are linear equations. So you can find the conjugate of this and write them in the matrix form, and you can find your result. Let me write the result here. Omega 1,4 will be you can check this from Eres Hoca's transparencies actually.
That's a double dot of S43, right?
That's a single dot. Okay. But for the acceleration, we have to take the derivative of the velocity equation, which is let me just, so this is the result, but I advise you, please have a look at the Eres Hoca's notes, because I cannot explain it in detail here. And for the acceleration, you will take the derivative of the following. IS12 dot equals I omega 1,4 to the I4 plus I S3 plus I S43 dot e to the I. We take the derivative, which gives you, of course, terribly long expression. Let's just correct this, right? Well, collect the terms, right? IS1 to double that. Okay. So what are these? This is acceleration of A3 equals acceleration of A2. This is the acceleration of A4 tangential. This is A4 normal. Acceleration of A3 relative to A4. And this is the Coriolis. Now this equation, you have to take, in order to solve for the unknowns, which are S43 double dot and alpha 1,4. Okay. You can take complex conjugate and solve for these variables, and you will find the results afterwards. Well, I'm not going to write them. Even writing them is quite long, so I'm not going to write them down. This one too is given. So results are, let's say, slides. So check them out, please. I'm not going to write them down, which is a lot of time-consuming work, but rather straightforward. Well, it took more than I had expected. I thought I would finish this in at most half an hour, but drawing and explaining was not very easy, this mechanism. Do you have any questions? If not, let me stop the recording.